Welcome back, and this is Professor Bright. This time we're going to look at series. And so you've seen these pop up in algebra and pre-calc for sure, but now we're going to look at them through a calculus lens. So we want to talk about partial sums and really talk about infinite series in ways that we haven't before, and discuss that idea of convergence or divergence having just come off of sequences. And then look at geometric series and see some nice applications related to all those. Okay, so to start off, just a reminder that we looked at a sequence, right? And we can represent it in using this notation. And again, sometimes you might also see us do notation like n is equal to 1 to infinity as kind of superscripts and subscripts on there as well. But if there aren't, assume it's infinite. Okay, then we want to determine a sum of the sequence members, so that's when we get a series. So we add a1, a2, a da 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 up to an and so on, and we can write that as an infinite sum using sigma notation, as we've seen before when we were talking about limits. So sum from 1 to infinity of the sequence an. Okay, so we've seen this certainly probably with finite series, and back when you were doing pre-calc, you certainly looked at, arithmetic series, something like this, and you said something like k is equal to 1 to n of like 3k plus 1. And you talked about formulas to find those. Well, now we're just saying, well, we're going to say n can really be anything up to infinity. And so we want to see, okay, well, if we go off to infinity, does that converge or not? Okay, but we're going to mainly look at some nice cases of infinite series. Okay, so we're looking at how series change, and we want to look at end behavior and all that. And to begin that analysis, we're going to look at what we talk about as partial sums. So just making it a finite sequence for a minute and then using calculus to take that off to infinity. Okay, and we did note the first partial sum of the first k terms is s sub k, so it just means add terms 1 through k together. So to find the first four partial sums, so this would be S1, S2, S3, and S4. Okay, I want you to pause the video and see if you can find these yourself. And here's what I got. So the first term is just 1, okay, and then 8/5, 1 plus 3/5. And notice here I just have a couple different representations. I have a1 plus a2, or you can say it's s1 plus a2, right? s1 is the same as a1. And then s3, we take s2, 8/5, and add on a3, which is 9/5, or 9/25 rather. So we get this. And s4 is s3 plus a4, and that's what I got when I calculated it out. Okay, so we can look at this, and then we eventually want to make some conjecture about whether this is going to approach a single value or not. Okay, and so that idea is convergence. Okay, and if we looked at the values numerically, they approach 2, and then they get a little bit bigger, but the differences seem to be leveling off. And we just want to know, is it going to converge or diverge? And so we would say that the infinite series, the whole thing is going to converge if we look at the associated partial sum sequence, and say that partial sum is finite, okay, and or as we go off to infinity, and we also have the sequence on itself is convergent. Okay, so really we would say that the series is convergent if the sequence is convergent and the partial sum, the limit of the partial sums is finite. Okay, otherwise we say it's divergent. So if we look at this, is it going to converge? Well, let's see if we can use the definition here. If we look at an, that's the sequence 3/5 to the n minus 1, and as we go to infinity, that'll go to 0, so that seems to be true. So this implies that an is convergent. Okay, so we have our first condition satisfied, and then what about the limit of the partial sums? So we want to look at the limit of Sn, and this is going to be the limit and I should say as n goes to infinity, as n goes to infinity, of, and then we want to look at the partial sum, so this is going to be the sum from k is equal to 1 to n of 3/5 to the k minus 1. Well, I don't know what that is, okay? So just a reminder about geometric series, which this one is, if we have something, and this is for an infinite geometric series, this is a finite geometric series, so we can maybe review your pre-calculus to look at the formula for a finite geometric series. But for an infinite geometric series, if we have the common ratio that r value is less than 1 in absolute values, then it's going to be convergent, and we can actually find its sum. And otherwise, the series we can say is divergent. Okay. Backing up just for a minute though, because we have for this last example, because an approaches 0, so the sequence, we have convergence for the sequence, and we do have the limit of the partial sums is going to exist as a finite number. It will, so the whole series will be convergent. Okay, its value coming soon. Okay, so this next part is going to be a proof. Okay, so we want to, let's see, so the series is convergent and we want to find its sum. Okay, to prove this, I'm going to use that above definition here. Okay, so for a convergent series, I need the sequence is convergent and I need the limit of the partial sums to be finite. So if I look at the sequence, right, an as a r to n minus 1, okay, and we know that this is convergent if absolute value of r is less than 1, which is true. So then that means that the sequence an is going to be convergent. So that's the first part of our proof. Now we're going to focus on the limit of the partial sums. And you've probably seen this before, but we'll just go through it again for fun. So we're going to let Sn be the series from I is equal to 1 to n of ar to the I minus 1. Okay, and if we were to write this out, this would be a plus ar plus ar squared plus ar cubed plus dot 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 a r to the n minus 1. Okay, and then what I'm going to do is multiply this by r. Why? It'll become clear in a little bit. So this would be ar plus ar squared, ar squared plus ar cubed plus so on and so forth up to ar to the n. Okay, and now I'm going to look at Sn minus Rsn. So effectively take this first one minus the second one. And if I do that, Sn, I end up with a minus ar to the n. Everything else would cancel. Okay, and so then if I do a little bit of algebra, we can, say Sn, so factor out an Sn, and then you could divide all that. So let's see, we can write this as a, and then factoring the numerator, a times 1 minus r to the n over 1 minus r. Okay, that's your formula for a finite geometric series. Oh, look. Okay, and now I just need to take the limit of this. The limit as n goes to infinity of Sn is, and if we think about this, r to the n, r is going to be your common ratio, and we know it's less than 1. So as we go off to infinity, this is just going to approach a 1 minus 0 over 1 minus r, which is a 1 minus r. Okay, so then this is a finite number, and therefore the sequence, or the series rather, n is equal to 1 to infinity of ar to n minus 1 is convergent. So we have that the sequence is convergent, and we have the partial sum, the limit of the partial sums is finite, so therefore the whole thing converges. And also, as a byproduct, we get out the formula for the infinite geometric, or for the sum of an infinite geometric series where the common ratio is less than 1. Whew! Okay, so long first video, but it does cover most of the essentials, what a series is, and really the definition of a convergent series. And next, we'll put this into use.